Alright guys, so we're going to start by talking about how it all began in Earth science here. Um, and we need to talk about how the universe came to be. But before we do that, I want to kind of give you a scale of everything, just a really brief uh, idea. So you're standing on Earth looking up at the stars. You are pretty much staring at all the stars, or not all the stars, but the stars in the Milky Way galaxy, our galaxy, a pretty large galaxy. And we're looking at about 100 billion stars in our galaxy. But if you back up even further, we are just one of a cluster of galaxies called the Local Group, each with its own 100 billion or more stars. And we can even get into superclusters. Each one of these is a galaxy in itself with billions and billions of stars. Or we can even back up really far and see this kind of filaments of galaxies and superclusters of galaxies throughout the universe. All right? So if you can just imagine, probably millions, if not billions, of galaxies, each with hundreds of billions of stars in it, and it gives you kind of a sense of awe of what's going on. But we need to take a look more precisely at the Big Bang Theory and how it all began, how the universe as we know it today came to be. And the first thing I want to do is kind of get out of your head that the Big Bang is an explosion out from a single point in space. It's more of an expansion. The Big Bang Theory, the name itself is kind of a misnamed theory. If anything, it should have been called the Big Expansion. Because an explosion, a Big Bang, indicates that the universe exploded all the bits and pieces out into an already existing space. But what really happened is our universe expanded out, and the space in our universe was a part of that expansion. Alright? So you kind of look at it like this. You have this singularity, this single point right here where everything expanded out from. And to this day, our universe continues to expand. It's actually speeding up in its expansion and becoming larger and larger every moment. So how do we prove this? That's the question. And we really have two pieces of solid proof to support the Big Bang Theory. Alright, as the picture shows, the proof's in the pudding here. And we're going to start with the redshift. We need to discuss a few things, though, before we really get into what redshift means. First is this, the electromagnetic spectrum. And what this is showing is different wavelengths with increasing or decreasing energy will produce completely different types of wavelengths. You have gamma rays, X-rays, UV rays, the stuff that give you sunburn, visible light. So all kind of here to give you sort of the easy rendition, that radioactive gamma rays, the ways we look at broken bones with the X-rays, all the way over to the radio waves and the microwaves, each with increasing energy as you move to the left and decreasing energy as you move to the right. So, and we're going to just kind of get at a couple of words here and definitions, nothing too difficult. A wavelength is just the distance between the crest of two waves. So if we go look at something that has a shorter wavelength, it just means that the crests are closer together and they're more intense. If it's a longer wavelength, it's a less intense wave, they're further apart. And we typically, because waves are so small, we measure those in nanometers, very small sections of measurement. Now back to this. So you can see over on the left side the gamma rays, X-rays, very intense, short wavelengths. The radio waves much longer. But I'm more interested in this middle section, the visible light. All right, and the visible light is what we see. The rainbows, all the colors that you can see, is a part of that visible spectrum. All right, we could take the white light that we see in the room or coming from the sun, and we can split it through a prism into all the constituent parts, the Roy G. Biv, the red, orange, yellow, green, blue, indigo, and violet. But more interestingly is when you look at these, the corresponding colors appear this way to our eye and to our brain because our brain is seeing the wavelength. The longer the wavelength, the more we are seeing colors that are reds and oranges. The closer the wavelengths get to each other, our eye and correspondingly our brain perceives the blues and the purples. This is kind of a weird way of thinking about things, that we don't actually see colors, we see wavelengths, and our brain interpret those wavelengths as the different colors. All right? So we'll come back to here, and you notice as you look at this, the blues and the purples have a much shorter wavelength, 400 nanometers. And as you move to the right, the oranges and the reds have a much longer wavelength, around 700 nanometers. Alright, so kind of break away, keep that in the back of your mind for a moment. We'll break away from that. I want to talk about something different now, the Doppler effect. It's actually not different, but this will all tie together. The Doppler effect is something you've known about for a long time. A car goes racing by, and you can experience the Doppler effect because as it comes towards you, the car, the sound gets more intense, and as it goes away, it gets less intense. What's happening is, as this car is coming towards you, it is speeding into its own sound waves, compressing those waves together, making it sound more intense to you. As it goes by you, the waves are getting stretched out, making it much less intense. That's the Doppler effect. Now we can take the Doppler effect, and instead of sound, make it what we see, visible. And so if something is coming at you, and those waves are getting compressed, and they're closer together, you could turn that into a color, blues and purples. And so if you see something that's blue, that means it's moving towards you. As it moves past you and moves away from you, and those wavelengths get stretched, you're going to see oranges and reds. So if we were able to turn sound into color, we would know if something was moving towards us by it being purple or blue, and if something is moving away from us by it being red or orange. Alright, you can see it here. Same applies with a galaxy. If we're looking at a galaxy, and that galaxy is moving away from us, the wavelengths are being stretched, and we would see it as being red. Right? If it's moving towards us, the wavelengths would be getting compressed together, and we would see it as being blue. So we can tell if objects in space are moving away or towards each other, ourselves. All right, take a minute. I thought this was funny. Most people now you guys can look at this bumper sticker and think it's funny too, or at least understand it. Most people probably wouldn't understand it, right? So here's where it gets interesting. You look at a galaxy and it just looks like white light. But if you look at it through a special instrument called a spectroscope, here's a very old spectroscope. What the spectroscope will do is it'll break that white light up into the visible spectrum, the Roy G. Biv. Now if you look at that galaxy, now and then come back and look at it again a year later, what you'll notice is all these little black lines, the spectral lines are called, will begin to shift in one direction or the other. Now if the galaxy is moving away from us, all those black lines will begin to shift towards the red side of the spectrum. If the galaxy is moving towards us, they'll begin to shift towards the blue side. And what this gentleman, this scientist named Edwin Hubble, you've all heard of the Hubble telescope, what he discovered some time ago is that when he looked at different galaxies through a spectroscope, he noticed that pretty much every single one of them was shifting towards the red side of the spectrum, which meant the galaxy was moving away from us. All these galaxies moving away from us. Well, if all these galaxies are moving away from us, and Hubble said, well, if you could stop them and rewind it all the way back to where they meet, that would prove that our universe is expanding, and it's expanding from a single point, a singularity, which eventually became known as the Big Bang Theory. Everything is expanding from this one location. So that's called redshift, and redshift supports the Big Bang Theory. Right? Hubble also kind of took a step further, and he said, okay, you take the current expansion rate, how fast the universe is expanding, all right, and it gives you an idea that the universe is about 10 to 20 billion years old. You look at the oldest stars. We know the oldest stars are between 11 to 18 billion years old. What's our best current estimate of how old our universe is? How long ago was everything at that singularity and has been expanding from since? We see it as 13.4 billion years old, give or take a little. Some people just kind of estimate it as 15 billion years old, 13.8, 13.7. We're talking give or take a couple billion years. The other piece of evidence was cosmic microwave background radiation. This was discovered back in 1965 by these two gentlemen right here. And there was another piece to this whole Big Bang theory. It was proven that the universe is expanding, but some scientists said, yeah, but if this is truly the case, then there had to be energy pushing that expansion. And where is that energy? And these two guys found the energy. As they looked out to space, they noticed there was an evenly distributed energy, low-level energy, all over the place, and they kind of were able to map it out like this. This is all energy spread evenly throughout space. That's the leftover energy from the Big Bang that caused that initial expansion. Now, I kind of like to talk about this just because it's interesting, and we've talked about the Big Bang theory, the two proofs now, and we'll do some labs and some experiments in class to help us understand that even better. But possible fates of the universe. Some people believe this right here, that the Big Bang caused, there's a big expansion, and just like throwing a baseball up in the sky, eventually gravity's going to bring it back down to Earth. Well, some people believe that the gravity of that expansion is going to eventually run out, and it's going to get sucked right back into that singularity called the Big Crunch. Not very ingenious names there, but so that's one idea. The other one is this one, that you get a big expansion, the Big Bang, and it's like throwing that ball in space, and the upward force on that ball is equal to the downward force of the gravity pulling it to Earth, so it never actually comes back to Earth, and the universe eventually stays the same size. Here's the one right here that we believe is probably the truest of the three. Most scientists agree with this one, the open universe, that the Big Bang caused this expansion in the same way that you throw a ball into the air, but if you throw the ball hard enough that the gravity can't pull it back, then that ball will expand out and will go into space forever. The theory here is that the Big Bang had enough force behind it that it'll expand forever. They'll never come collapsing back. Well, if there was a recollapse, if there was a big crunch, then here's the events you'd see 70 million years from now. Or 70 million years before the big crunch, sorry. Sky temperature, 300 Kelvin, very hot. We wouldn't survive that. A million years before the big crunch, 3,000 Kelvin. The nighttime sky is as bright as the sun. 3 weeks, 10 to the 6th power Kelvin. That's 10 with 6 zeros after it. And 3 minutes, 10 to the 10th power. In other words, everything's crunching back into that small little space, that very dense, very hot pre-universe singularity. Here's probably what's really happening, that the universe is going to expand forever. In fact, we thought for a long time that if the universe was going to recollapse on itself, then just like that ball thrown up into the sky, it would slow down, slow down, slow down, come to a stop, and then collapse back to Earth. Well, we expected our universe to be, the expansion to be slowing, and it's not. In the last decade or so, we found out that it's actually speeding up. So it could be expanding forever. What happens? 10 to the 12th years from now, all the stars run out of hydrogen, leaving, just white dwarfs, neutron stars. Basically, the stars are old. 10 to the 27th years from now, most objects are being pulled into galactic black holes. 10 to the 31st, most galactic black holes merge to form supergalactic black holes. 10 to the 67th years from now, this is a long ways into the future. But most black holes are evaporating. And, with everything spreading, the universe is becoming very cold. 10 to the 97th years, the galactic black holes are evaporating. And 10 to the 100th years, supergalactic black holes have evaporated. And I like this quote. Good Robert Frost quote. Some say the world will end in fire, others say in ice. A very cold ending if the universe expands forever. And that's where we'll end today, and we'll pick up on another lecture in the future. Bye-bye.